Alright, so let's talk some about aromatic synthesis. Now we've talked about this in class a little bit already. For example, you guys will know how to take just benzene and make a mono-substituted benzene derivative from it. In this case, of course, it would just be bromine and iron 3 bromide, for example. You also know that if we want to take benzene and react it with something like this, that we can make a particular product from that. In this case, we get this sulfonic acid. All right. Now, making di-substituted benzene rings. All right. Well, let's talk about that. Now, we talked about this a little bit before as well. We know some groups are orthoparadirectors, some are metadirectors. You'll remember methyl groups, or indeed all alkyl groups, are orthoparadirectors. Nitro, for example, is a meta. We also know that Friedel-Crafts reactions don't work well with highly deactivated rings. But when we look at this, we'll see that whichever one of these two groups we put on first has to be able to direct the other in the desired position. So, for example, if we were to put the nitro group on first, and we could get the methyl group on afterwards, can you see the methyl group would go meta to the nitro? If it was to go on, which it probably wouldn't. If we put the methyl group on first, then because it's an orthoparadirector, it will indeed direct the nitro group where we want it to go. So in other words, we can say, well, I'm going to start off with my benzene, and I'm going to do whatever reaction it is that I need to do to get to my methyl group, which is a Friedel-Crafts alkylation, so I would just use my alkyl halide and my either AlCl3 or FeCl3 catalyst, and get out my alkylated benzene. This will be toluene, of course. Now, because toluene's the orthoparadirector, I can just use my two reagents to get the nitro group on, and of course you know that is nitric acid and sulfuric acid. And that takes us right to our desired product, which, if you think about it, whilst I'm finishing off the structure here, what's the name of this? Well, of course, it's toluene with the nitro, so it's para-nitrotoluene. Now, this is only the first part of aromatic synthesis, however, and you've seen all of this before. What if we were to make things a little bit more complicated? All right, somebody keeps texting me lately. I don't know who that is. Well, actually, I do, but bollocks. Okay, so when we look at this guy, this is a di-substituted benzene ring. Chlorine, you guys know, is an ortho-paradirector. Come on, dude. Why aren't you showing up in the color you're supposed to? All right. And we know the sulfonic acid group is meta. So which one do we put on first? Well, given that they're meta to each other, we have to put on the meta director first, which would be the sulfonic acid. We put that on first and then put on the chlorine afterwards. All right. Now, when we come down to here, you may notice that, well, we've seen a reaction to put a bromine on before, but we haven't seen a reaction to put specifically an NH2 group on before. Now, this is aniline, so there must be a way to do it. And it turns out there is a way to do it. And the aromatic synthesis routes document I gave you all that has all those synthesis routes on it, this indeed is one of them. It shows you a way to put an NH2 group on. And you're going to see there's a whole bunch of groups you can put onto a benzene ring, but you can't put on directly. You have to put on via some other group. All right, and the amino group is one of them. All right, the amino group will only go on by way of another group that has a nitrogen in it, which is the nitro group. All right, so if I put my nitro group on first and I get out my nitrobenzene, then, okay, if I was to ask you, well, going from here to here, this being aniline that I'm about to draw out, can you see that if we make this change, we go from something that's a meta-director to something that's an ortho-para-director? So just changing this group can change the complexion of your molecule completely. So I'm removing oxygen, I'm adding hydrogen to make this reaction go. So what sort of a reaction do you think that would be? Well, if you said a reduction, you would be absolutely right. And in fact, this reduction can be done several ways, but one simple way to do it is with the addition of hydrogen over a palladium and carbon catalyst. In fact, you would have seen this before in the reduction of alkenes and alkynes to alkanes. All right, this will also reduce a nitro group to an NH2. So if we look at these two compounds here, notice how they're very similar. They're actually isomers of each other. This is meta-bromoaniline, this is para-bromoaniline. Obviously we know what the reagent is to get the bromine on. The question we have to ask ourselves is, well, in what order do we do all of our reactions to get what we want to get? So when we look at let's do this top one first, okay? Bromine, you know, is an ortho-para-director. The amino group is an ortho-para-director. So your question might be, well, hang on. If both my groups are ortho-para-directors, how can I possibly make this? Well, you're forgetting to take into account that the NH2 can't be put on directly. It has to be put on via the nitro group, which is a meta-director. So hopefully that may tell you, well, what do I have to do first? I have to find a way to get my two groups meta to each other. So the first thing I can do is I can say, well, I know I can make my nitrobenzene. All right. Now I know nitro is a meta-director, so if I then do my bromine with the catalyst, what happens is I'm going to put my bromine meta to my NH2, to my NO2, I'm sorry. And then after I've done that, all I do is the reduction reaction that we did here to reduce the NO2 group to an NH2 and keep the bromine where it was. All right, that's how we can put the bromine and the amino meta to each other. Now for here, both these are ortho-para-directors, as we said before. The one thing we hopefully do remember is that NH2 is such a strong ortho-para-director, though, that it will direct to each of the ortho and para positions if we add a bromine on. So we don't want to do it that way, but we can add the bromine first, because we know that bromine's an ortho-para-director as well. So if I put on the bromine first, what I'll get out is, and I'm just going to draw the bromine on the bottom here just for the sake of simplicity. I have this, and then I can do my two sets of reagents to get to the NH2, which is these two steps here. I can do my HNO3 H2SO4, essentially we call that step 1. That will get us to the para bromonitrobenzene, and then step 2 would be that reduction to get us to the para-bromoaniline. So the point that I'm trying to make here is, depending on the structure of your compound, the order in which you do your reactions is really kind of important. All right. Now, okay. So what if I want to do a reaction kind of like this? I want to take benzene and make bromine and cyanide. I've not seen cyanide before. Well, obviously I have, but maybe you guys haven't. How do we put cyanide onto a benzene ring? Well, we haven't seen that before either. Well, if you've prepared for the class, then you will have seen it before. So it turns out cyanide, just like the amino group, is again one of those groups you cannot put onto a ring directly. There's no mechanism for it, but there is a way you can put it on via some other group, and I'm going to go through that. If you've done the prep for today and you've looked through the aromatic synthesis routes, then you'll see there's a particular group you can put onto a benzene ring that then gives you a whole host of opportunities for other groups to add on, and we're just going to run through that right here. We're going to start off with putting a nitro group on. We're going to reduce it just like we did over here to an NH2 group. So I'm going to make an NH2 here. This again is our reduction. Now what I'm going to do At this point, this is a particularly important step. I'm going to use, well, let's see, who remembers the name of this? NO2-. It's a polyatomic ion. It's either nitrate or it's nitrite. Which one do you remember it is? Well, if you said nitrite, you'd be right. This is sodium nitrite in HCl. And this makes a very particular compound. And I'm going to draw the structure out. It's got this triply bonded species called a diazonium salt. And the reason why this is so very reactive is that this N2 group is so willing to come off as nitrogen, which is a very stable molecule. This is so reactive that you can then react all sorts of compounds in here and put on a variety of different groups, one of which is cyanide. Alright, so again, if you look in your aromatic synthesis routes documents, you'll see there's a bunch of molecules you can use here to put different things onto a benzene ring. One of those is copper 1 cyanide, which allows you to replace via a different mechanism than what you've seen before the diazonium salt with the cyanide. All right. So how would we use this reaction to make this product? Well, again, we just want to look at our directors. Okay, bromine we know is an ortho para director. Cyanide, well, what's cyanide? Well, if you think about it, cyanide is C triple bond N. And that fits into the category of compounds that have a pi bond coming off the benzene ring. Those are meta-directors. They're deactivators. Okay. So the question then becomes, well, which one of these two do we want to add on first? Well, of course, it's the cyanide, because the cyanide is the meta-director that we can then add the bromine to. So we can go through all these steps to get to the benzene with the cyanide on it. This is called benzonitrile. And then we just do our one reaction that we know is going to put bromine on, Br2 FeBr3, and that is going to, because our cyanide is here, it's going to put our bromine meta to it. It's going to give us this. Now I just want to make sure that everybody can see that this is exactly the same thing as this. Okay? Just kind of rotated 60 degrees. It's exactly the same thing. Alright, does that make sense? Okay, so this diazonium salt and the method to get to it is very important. There's all sorts of different groups you can put onto your benzene ring this way. Okay, a couple more reactions. This is the last slide. What reaction is this guy here? Well, this is the Friedel-Crafts acylation, not acylation. This is the acylation that allows you to make a ketone. Now, a ketone here, what sort of a director is this ketone? Well, hopefully you would have said meta-director, because it is. Now, what if you wanted to have a group para to this one, and this was already on here? Well, one thing you can do is convert this into an ortho para director. Now here, when I go from here to this butyl benzene, I am removing oxygen. I'm replacing that oxygen with hydrogen, 2 hydrogens here. This again is a reduction. This is the use of HCl in the presence of a zinc and mercury catalyst. All right. So this goes from a meta to an ortho para director. So notice I've got 1, 2, 3, 4 carbons here, and I've got 1, 2, 3, 4 carbons in the product as well. One other useful thing about a reaction like this is I can then take this and I can do something very specific to it. I can take a compound like this, or really any benzene ring with any alkyl group on it, provided there's at least one benzylic hydrogen, and benzylic hydrogen is the one coming right off the benzene ring, and I can oxidize it with a compound that you guys have seen before called potassium permanganate, and I can cleave right here and I can oxidize, and no matter how long this carbon chain is, whether it's 2 carbons, 3 carbons, 15 carbons, provided there's one benzylic hydrogen there, the product I always get is this. Now this is benzoic acid. You've seen this before. So this is another example of a group you can't put onto a benzene ring directly, but you can get there via something else. All right. We could also get there from something like toluene, for example. Right. I could take toluene and oxidize it in KMnO4, and it would get to the same benzoic acid product. So let's just apply that. Look at this compound here. I have para-nitrobenzoic acid. Now, the acid group is a meta-director. The nitro group is a meta-director. The nitro group slows down the reaction so much that Friedel-Crafts reactions don't work, so we couldn't put the nitro group on first, which implies that we've got to put this group on first. But if this is a meta-director, how do we get this meta to it? Well, of course, just as I said, this guy doesn't go on directly, it's got to go on via an alkyl group. And if we're going to make an alkyl group, why not make the simplest alkyl group we can make? Let's just make toluene. All right. So I'm going to make toluene, and for that I need my Friedel-Crafts reaction. So I'll just CH3Cl and something like AlCl3. And from that I'm going to make my toluene. Now, it's at this point I have to decide, well, what do I do next? Do I oxidize my methyl group to the acid, or do I nitrate this and put on the NO2? Well, can you see that if I oxidize my methyl group to the acid, this is a meta-director, I can't get my NO2 where I want it. Methyl, on the other hand, is an alkyl group, which is an ortho-para-director, so I should use that ortho-para-directing ability whilst I've still got it. So in other words, I want to, right now, when I can, put that NO2 group on before this group is turned into something that's a meta-director. Now the reagents for this, as hopefully you remember, are nitric acid and sulfuric acid. So now I've got my methyl and my nitro groups para to each other. I've got para-nitrotoluene, and then I can just oxidize it in the presence of KMnO4. That doesn't do anything to the nitro group, it just oxidizes the methyl to get to that. Now these are just several examples of aromatic synthesis. There's a whole bunch of others, but hopefully this makes things a little bit clearer. Thank you.